Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for students going through integral calculus and currently going through integration techniques, specifically trigonometric substitutions. Now, I don't want to give you the key to this by saying that you're in Trig Subs, but honestly, this type of example is often done in a Trig Sub section. So let's go ahead, and by the way, this is only going to be a single example video, so very fast here. Let's list out our possible techniques. So here we have them right here. I just listed them out kind of in the way we learn them. You have direct integration, which just means you have something like the integral of the sine or integral of e to the x or something like that, which we don't have. Or we could do a u substitution, and that's pretty much all of the other techniques that you know up to this point other than by parts. U substitutions are, well, typically just u subs, but there are other kinds of specialized substitutions, ones that where we force even powers on trig functions. That would be if you have the integral of, say, sine cubed of x times cosine to the 10th of x dx. You would do a smart substitution here to force this odd exponent to become even. And that smart substitution in that case would be the cosine substitution. It would steal away a single power of the sine. But again, that's not what we're dealing with in this example, so I'll erase it. We also have a brand new type of substitution called a Trig Sub, and that's where we see sums or differences of squares. And again, let me just zoom out here and showcase, well, we really don't have a sum or a difference of squares that we can see there. And then finally, we have by parts. And by parts is useful when you have a product of functions where both of those functions are different kinds of functions, like an exponential and a trig, or a trig and a polynomial, or something like that. It's also incredibly useful when you just have the integral of, let's say, a single function that you don't know the antiderivative of. Sometimes by parts can be used in those situations as well. Going through that list, it seems as though none of them fits the bill for integrating this. However, I will say that this is actually a sum or a difference of squares. You just have to be willing to complete the square to see it. So that's a very common technique when you have a radical that involves a polynomial, specifically a quadratic polynomial, and you have no other method or technique that'll work. Try completing the square. And by the way, when you try to complete the square on this guy right here, it is very important that you practice good algebra. I start by factoring a negative off of both terms, and now I'm going to just reorder those terms within the radical. That grouping symbol is incredibly important. I get on students' cases all the time about making sure they use grouping symbols, because when they don't, things go terribly wrong. And at this point in mathematics, I should never have to say that. You should be okay with using grouping symbols and distributing negatives properly, all that fun stuff. But I'm just saying it out loud for those who still make that silly style of mistake. Now let's start the completing the square process. And I'm somewhat long-winded with it because I've been teaching for so many years that I just have a habit of taking my time with it. You take half of that coefficient of -1, and you'll square it and add that as a third term on that trinomial or on that quadratic expression. Of course, that green ink was not there to begin with, so we need to offset that green ink. Again, a very tragic mistake is for people to say, oh, that means I subtract -1/2 squared. And that is not actually the case. And that's because you're not adding a -1/2 squared, you're actually subtracting a -1/2 squared. So to offset that subtraction of -1/2 squared, you will add back a -1/2. squared. Finally, as part of the completing the square process, I will go ahead and write that trinomial as a perfect square. There we go. We have completed the square, and you can actually see, if you were to reorder this addition, that you actually do have a difference of squares. It's this first object squared minus this last object squared. And if we look to our Trig Sub material, when you have a difference of squares, you have a couple of options. You're either going to be looking at a number squared minus a variable squared, or a variable squared minus a number squared. They're both completely different situations. Well, lucky us, what we have is a number squared minus a variable squared. So we are going to go ahead and do the substitution so that we eventually get 1 minus sine squared of theta. Now, if you take a look at our integrand, specifically the radicand itself, I sort of want this to eventually become a sine squared of theta. But if I just made that substitution, that if I said x minus 1/2 squared is the same thing as sine squared of theta, well, I wouldn't have 1 minus sine squared of theta, I'd have 1/4 minus sine squared of theta. And I don't want that. So what I'm going to do is actually allow 1/4 sine squared of theta to be that picture right there. And that's so that when we substitute that in, we can factor out the 1/4 from the first and second terms within that radical. And before I go through and do the substitution, I do want to make some mentions here. First of all, my real substitution is not this, it's actually the square root of both sides of this. A lot of people get a little bit confused when I just take the square root of both sides and I don't have a plus or a minus. And the reason why I don't have a plus or minus is that my true substitution is actually that x minus 1/2 is going to be traded out for a 1/2 sine of theta. If you can imagine that I trade out this x minus 1/2 for a 1/2 sine of theta, when I square it, I get a 1/4 sine squared, and now I can factor out the 1/4, and I'll get 1 minus sine squared, and everything's peachy keen. So honestly, that second line is my true substitution, and I squared it right here so that it makes it easier for me to substitute it in. That's all. Now let's go ahead and find out what dx is. Well, that's very, very nice. So I know that I'm going to replace my dx with this picture right here. I'm also going to replace this x minus 1/2 squared with this picture right here. And we still have to worry about the limits of integration. And this is a great example to showcase that when you do perform any type of substitution, you should change your limits of integration as well. I'll show you why. If x is 0, well, I'll let x equals 0 in this equation. I will get sine is equal to a -1. And that implies, because we're taking the sine inverse of both sides to solve that, and sine inverse has a restricted range, that will imply that theta is equal to a -pi/2. Now let's go ahead and see what happens when x is equal to 1, the upper limit. Well, going back over here, if x were 1, we'd get the left-hand side to be 1 minus 1/2, or in other words, 1/2, and sine would then be 1. And that implies theta is pi/2. Now I have everything I need to make my full substitutions so that this integral never has to be rewritten in terms of x because it's definite and we can just transform it now into the world of thetas completely. Going back to black ink to do that. Let's see, we have the square root of 1/4 minus 1/4 sine squared. And remember, dx gets traded out for a 1/2, which I'll throw out front, cosine of theta d theta. We can factor a 1/4 out of that radical, take its square root, it would be a 1/2, multiply it by the half out front, and we'll get back to 1/4. Notice, by the way, on this second step here, I'm not writing theta equals -pi/2 to theta equals +pi/2. I just wrote -pi/2 to pi/2. That's because in this previous step right here, I have assured myself that everything is written in terms of theta. There's no need for me to tell the reader in then my next step that I am still in the world of thetas. Now that I have everything written in that world, I will assume that's the world we will continue to work in from this point forward. And of course, the square root of 1 minus sine squared is the same thing as the square root of the cosine squared. Square root of cosine squared is the cosine. Specifically, it's the cosine because of the substitution we made. Normally, and I say this in a previous video, so please watch my video on the reasoning why we don't have to worry about the absolute value sign, but normally this would be the square root of cosine squared of theta, which would return the absolute value of the cosine of theta. But there's something very special about the substitution we made that will always force cosine to be positive, so, or at least non-negative, so we don't have to worry about the absolute value signs on that. And if that square root is going to turn into a cosine times another cosine, we get a cosine squared. Now we take a look at this and we realize we cannot easily integrate a cosine squared, but luckily we have a power reduction formula or a half angle identity, however you want to state that. And that is going to be, now before I continue, I should tell you that the entire time you're doing this process, you should be looking at algebra, arithmetic, or trig before you move forward and do your calculus. Notice here that yes, I did a little bit of algebra right at the beginning. I didn't touch calculus until I got all the way down to here. At this point, I started doing a U sub. Well, actually I did a theta sub, but whatever. I did a substitution once I hit that green ink. But then after I hit that green ink, I went back to just doing trig. Now at this point right here, I could mention something kind of important. And so I guess I will mention it here. Cosine is an even function, and cosine squared is also an even function. So I could have inserted a step between this step right here and the step above to say, you know what that integral is? It's going to be twice the integral from 0 to pi over 2 of cosine squared. And to be honest with you, whenever I can get one of my limits to be 0, I rejoice. That is a good tactic. So I'll go ahead and make that modification down here as well. And 2 over 4 is just 1/2, so I'm cleaning that up right there. So I'm just letting you know, always look out for little things like that. Now, just a little bit of factoring, factor out the 1/2, and I'm going to split this integral. If you're one of my students, then you know I actually do tell you to think geometrically about your integrations. Specifically for trig functions, I think that thinking geometrically really helps out. So if you just consider what this integral means, you're finding the area underneath cosine of 2 theta from theta equals 0 to theta equals pi over 2. Normally, the cosine goes through a full cycle on the interval 0 to 2 pi. However, this too means that this cycle or this cosine function is going twice as fast. So it reaches the end of its period by the time pi, which means halfway through is time pi over 2. Now take a look at that function. The area up here and the area down here are the same. They will cancel each other out. So I know the integral from 0 to pi over 2 of cosine of 2 theta, that's just going to be 0. I don't actually have to compute anything. And that is a very powerful tool. I'll keep saying it the entire time that you're watching my videos in integral calculus because most people tend to avoid thinking geometrically. They just want to barrel through computations, but I'm telling you, it can save you a lot of time if you get used to it. So our integrals become this right here, 1/4 times theta evaluated from 0 to pi over 2 plus 0, and that's just going to be pi over 8. What a great example to demonstrate both your use of algebra and trig and your knowledge of symmetry. I hope that this video helps you out understanding at least little bits of integral calculus and integration techniques. I hope to see you in future videos. I hope you have a wonderful day. Be a good human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel listen close. Don't talk too much, that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.